Today I am going to discuss polymer reactions and their different mechanisms, where I have to go through the detailed discussions on the cationic polymerizations, what would be the anionic polymerization, free radical polymerization, Ziegler-Natta polymerizations of alkenes, etc. So addition and condensations has been already discussed in the earlier part, where addition is the single monomer unit have to be there for formation of a monomer, formation of a polymer without producing any side product. While in the condensations, there will be one or two monomers can be there, and formations of other part have to be there. That means side product have to be formed. So what are the cationic polymerizations all about, and anionic and free radicals? Let's discuss, go through all. Since we have already got free radical polymerizations in earlier part also, so first I would like to discuss the free radical mechanisms at the very beginning. So free radical mechanisms, what it's all about. So free radical mechanisms is generally due to the generations of a free radical where commonly using our peroxides will be there. So acetyl peroxide, tertiary butyl peroxides, which have been used for the same initiation steps where the free radical have to be formed. So here it is a 1-benzoyl peroxide. When initiated, it gives a phenyl free radical, which when react with an alkene part, they will form another free radical. Due to that formation of free radical, when it undergo another step, which is called as the chain propagating step, where it reacts with the double bonded alkene to form then propagations. These propagation chains can be terminated by the free combinations of the free radicals, which has been shown in the third step, where it is the formation lead to formation of the polyethene. So these are the way through which different sorts of peroxides have to be used as a catalyst. So earlier in the dibrugarh industry, there is a questions of azobisisobutyroitrile. What is the importance or the role of AIBN in the free radical polymerizations? So if a free radical polymerizations, it always have to be used as a free radical initiator, which have many importance or advantages over the peroxides one. Here I am showing the AIBN. When it on the applying the temperature near about 66 to 77 degrees centigrade, it forms the free radical. One is here, another one is this one. So that's why the importance of the role of it is simply to generate the free radical polymerization. In cationic polymerizations, the initiator is an electrophile that adds to the alkene, causing it to become a cation. For example, BF3, AlCl3, etc. What are the advantages of applying the Lewis acid is that it does not have an accompanying nucleophile that could act as a chain terminator, or would be the case with a proton donating acid such as HCl. So the cation formed in the initiation step reacts with the second monomer, forming a new cation, and then it will be proceeded. Similarly with third, fourth, and it will be continuation. For example, if a cationic polymerizations used only for alkenes that can give a tertiary carbocation on protonations, or a vinyl ether that can give a oxonium ion. Here it is the vinyl. When it is react with an HC, it gives a stable tertiary carbocation. This is the criteria to form, it should form a stable carbocation. Similarly, the cation intermediate for the vinyl ether is a stable oxonium ion, which has been shown here. So there is a criteria that the radical must be stable one for the cationic polymerization. So here it is the same initiation. So stable tertiary carbocation will be formed. The stable carbocation can be re-reacted with another monomer unit, followed by one another, followed by it will be with one another also. So it will always lead to formation of a tertiary carbocation. And when tertiary carbocation gets terminated, that means they will combine with each other. It will lead to formations of another compound, and that is the reactions leads to the formation of long chain polymers. So I can show it in another way also. Here it is the same initiating step where the Lewis acid react with an alkene part to form an carbocation. The carbocation again react with the another monomer unit to form another one. And similarly, it will be propagating one by one. And on that propagation's way, it will be leading to a huge number of carbon chain, which can be compiled up or terminated the chain by the loss, or either by the loss of proton, reactions with nucleophiles, or the chain transfer reaction with solvent, and can be there. So these are the way to the proceed for the terminations. So this is the slide where I am trying to show the Lewis acids act as a chain initiator with an alkene part. So where the first step shows the chain initiator, then chain propagations, and followed by terminations. In the termination step, there are the different way can be lead to the terminations. One, that is loss of proton. Second, reactions with nucleophile. Or third, that can be charge transfer reactions with solvent. So it is the hydrogen is here. So one hydrogen will be lose out. So nearby the hydrogen, say CH2, yeah, hydrogen one lose out. So formation of a double bond. Here one nucleophile attack the carbon, so that the new carbon nucleophilic bonds will be there to lead to the terminations. Here it is the positive, XY is the solvent. So when it comes to the carbon, it will form then another compound. So on the next, I am showing the anionic polymerizations. So on the anionic polymerizations, in anionic polymerization, the initiator is a nucleophile that reacts with the alkene to form a propagating site that is an anion. Nucleophilic attack on an alkene does not occur readily. Just listen carefully. Nucleophilic attack on the alkene does not occur readily because alkenes themselves are an electron-rich compound. The initiator must be a good nucleophile, such as sodium amide or butyl lithium, and the alkane must contain an electron withdrawing substituent to decrease its electron density. Some alkenes that undergo polymerizations by an anionic mechanisms are shown below. So here it is the same initiation step where the alkene part undergoes and same initiator due to the presence of an anionic part. When it formations, when it is the butyl lithium is there. So butyl lithium, when react the carbon, it leads to and formation of butyl to carbon chain. Then the chain, when it's propagated, it will react with another monomer unit to propagate, and the propagations can be terminated and formations of a different monomer unit, difference and polymer. The chain can be terminated by chain transfer reactions with the solvent or by the reactions with an impurity in the reaction mixer. If solvent cannot donate a proton to terminate the chain, And if all the impurities that can react with a carbon ion are rigorously excluded, the same propagations will continue until all the monomer has been consumed, and at this point the propagating site will still be active, so the polymerization reactions will continue if more monomer is added to the system. And such non-terminated chains are called living polymers. They can kill, they can even be active until they have been killed. So living polymers usually results from anionic polymerizations because the chains cannot be terminated by a proton lost from the polymer, as they can in the cationic polymerizations or by disproportionations or the radical recompositions. So these are the part of the termination process. Now, when I discussed about the cationic polymerization and anionic polymerizations, we have seen that substituent on the alkene determines the base mechanism for the chain growth polymerizations. So alkenes with substituents that can stabilize radicals readily undergo radical polymerizations. If an alkene having an electron with donating groups, it can stabilize the cation and hence it leads to the cation polymerizations, and vice versa for the anionic polymerizations. Let's find out a few examples. Examples where it is the cationic polymerization is one is propylene, phase one will be the stable isobutylene, then vinyl acetate, styrene, etc., which will lead to formation of a stable carbocation, and hence they will undergo the cationic polymerization. Similarly, I am just giving a few examples where they list out the following groups of the monomer in order of decreasing ability to undergo cationic polymerization. If you find out, here it is an electron withdrawing group, here it is donating, here it is donating. So due to the presence of electron donating nature, this one will be highly active for the cationic polymerizations. So this one is the least active for the cationic polymerization due to presence of an electron withdrawing group. So similarly, try to find out the others too. So similarly for the anionic polymerization also, here is vinyl chloride, that is the electron withdrawing group, here it is the electron withdrawing group, here is the ether group, which is an electron withdrawing group. So these are the parts of the examples in which the commonly active anionic polymerizations. And if you've been asked to find out the group of monomers in order to decreasing ability to undergoing anionic polymerizations, here is the way, that is the NO2, which is an electron donating, OCH3 electron, this one is donating, this one is withdrawing. So withdrawing one will be the faster anionic polymerization, so this one will be the fastest, and this one will be the lowest. Similarly, here also, you just find out CN is the electron withdrawing, Cl is withdrawing, but CH3 is donating. So this one will be the having the least probability to undergo the anionic polymerization. Now let's proceed to the Ziegler-Natta polymerizations. So propylene can be polymerized by the titanium or aluminum catalyst developed by Ziegler and Natta, and hence with their name, that the catalyst is commonly called as the Ziegler-Natta catalyst. The polymerizations always leads to the isostatic static, as they are the stereoregularity. So that means if I use an alkene and if I use the Ziegler-Natta catalyst, it will lead to the isotactic polymer. That is on the same side, or the isomeric will be same. All the chiral carbons will be same one. The mixed metal compounds. What is now the question is that what is the Ziegler-Natta catalyst? So it's a mixed metal compounds which is being formed through the reactions with titanium chloride and aluminium alkyl aluminum groups. So when they react, they give a compound which is the titanium sigma complex, and that react with and that gives that exchange an alkyl group by donating a chloride group to the aluminum. And here it is the compound, so it is the titanium, here it is the aluminum. The alkyl titanium sigma complex, this one, can form pi complex with the first molecule of propene and then carry out a carbotitanations of the pi bond. So here is the way how they are being reacted. So this establishes the first carbon-carbon bond. Now, insertions of the next propene will be continued, and it will be continuing, and accordingly it will form leads to the polymerization. So if I show it here, it is the vacant site to accept an alkyl group. So here the titanium trichloride, this one is the ligand. So here it is the way R will be attached here. Then it will be again here. So it will be continued. So let's see if these are on the same side. So this is the way. One question has been asked that the epoxides when react with an glycol, what polymer it will be. Epoxides when react with a nucleophile, here is the nucleophile. Oxygen, 2 dots electrons or OH will be act as a nucleophile. So which will influence to break out the epoxide. So leads to formations of an alkoxides as shown above. When the alkoxides react with another epoxide ring, it will undergo SN2 reactions as shown below. So that's the way to form an polymer. It will lead to the form of polymer. So I just request you go through the slides very detailed, and if you have any doubts, any problems, just call me.